Hello, class. I wanted to make this video for you before our next class, Data Analyst Part 6, to try to help walk you through the basics of regression analysis. I know I introduced this concept a little bit today or in a previous class, but hopefully this video helps solidify additional understanding of what we're going to be trying to do in this upcoming class. So there are many different types of regression models that we can potentially work with. So some of these examples include a linear regression, a logistic regression, and a ridge regression. There's others beyond that. The primary two that we're going to be working with in this class is a linear regression and a logistic regression. Okay. So the basic purpose of any regression model is we're trying to identify a statistical and economical relationship between two or more variables. So in this assignment, we're just going to learn the basics of a simple linear regression, which is a regression model with only one explanatory variable. So we're going to always have our dependent variables, which is what we're trying to understand gets influenced, how it gets influenced, okay? And so the explanatory variable that we're interested in is we want to know how it explains our dependent variable, right? So that's essentially the relationship that we're going to be analyzing in this video, okay? So during class, we're going to cover a multiple linear regression, which is a regression model with multiple explanatory variables, so more than one. We're just doing one in this video, and a logistic regression, which is a regression model when our dependent variable is binary, so equal to 0 or 1, okay? So to get started, let's import our pandas and our common pandas options, along with a few other modules we'll be using, okay, like matplotlib and numpy. Load those in. So let's get back to the basics now. And you might recall from your algebra class way back when in junior high that the formula for a line is typically written in the form of y equals mx plus b, where m represents the slope of the line and b is the intercept. Okay, so in the following example, the line has a slope of 2 and an intercept of 5, meaning it's going to start at 5, cross the y-axis at 5, and slope through it with 2x, okay? So let's view this graphically in the following figure. Don't worry about this code. It's just here for our discussion. So here's the figure. And as you can see, we have an intercept at 5 and a slope of 2. So what this means is that for every unit increase of x, y increases by 2. So as x goes from 0 to 1 down here, y is going to increase from 7 or from 5 to 7. And then 1 to 2, y will increase from 7 to 9. Okay. So what happens when we change the slope and the intercept? Okay, so now I'm going to produce a couple of more figures and walk through each of these and how they're different. Okay, so here's our first one, so we can use it as a benchmark of a comparison. But if we change the intercept to 10, notice our green line just shifts up five places, but the slope is the same. Same thing with y equals 2x minus 5. Our slope just changes down to -5, okay? Or not our slope, but our intercept, okay? Additionally, in this new figure, now if we shift the slope to 4, you'll notice that the slope is becoming steeper because it's increasing, meaning for every one increase in x, y is going to increase by 4. Hence, they both cross the y-axis at the same intercept, our original formula and the new one. However, the slope is much steeper here. So as we move from 0 to 1 in x, y is going to increase by 4 rather than increase by 2, which it was doing in the previous equation. Similarly, if we don't have any slope at all, so the slope is equal to 0, it's essentially going to produce a horizontal line at 5, which is what our red line is here. And similarly, if we have a negative slope, and so in this case, -3x plus 5, we're still going to cross the intercept at the same, or cross the y-axis at the same intercept, but our slope will be downward rather than upward because we have a -3x. Okay. So with linear regression, we use a similar notation, but we use Greek symbols rather than letters as this is just the default or customary with linear regression models. So in this case, y equals alpha plus beta x. The alpha symbol is the intercept and the beta symbol is the slope. Okay. The linear regression is now seeking to find the parameters of alpha and beta that are going to best fit our data. So let's use an example of a linear regression. Okay. So below we have data for 20 students enrolled in accounting 526, which includes each student's final percentage grade and the average number of hours worked each week during the semester. So what we want to know is if the average number of hours worked per week is statistically related to the final grade received in the course, right? So we might predict that the harder you work, meaning more hours you work, the better grade you're going to get. Okay, so let's load that in and take a look at the data frame. Here we have our grades in percentage form and then the number of hours worked per week during the semester. Okay. So now let's plot the data and see if we can visually identify any relationship between the two. Here we're going to use a scatter, right, which is the correlation between two variables. Let's graph this and see what it looks like. So here there appears to be somewhat of a linear relationship, meaning that as you studied more, your grade went up, but it does also appear to be sloping downwards. And now that's partially because you can only go up so far, so we're capped at 100%. So of course, our trend can't always keep going up because it has to stop at 100, right? So there's diminishing margins of return for more hours that you study per week. Okay. We can now use this in a linear regression and define the line that best fits these data. Okay. So to do so, we're going to use the stats models to estimate the linear regression. Okay. So in other words, this linear regression is going to be an ordinary least squares, or OLS. I'll say OLS a lot, to obtain beta hat and alpha hat. The hat on each of these variables just means that they're the estimated from the data, right? So these are our estimates. Okay, they're predicted from the data. So first, we got to start by importing statsmodels.api. We typically import this model as SM for an easier reference in the code later, similar to what we did with pandas and NumPy and matplotlib. So let's load that in. We now need to specify the y variable, i.e. the dependent variable, and the x variables, which are going to be the independent variables. So in this case, we just have one. We have the y variable, which is our grade, and the x variable, which is hours. Okay, so we're only having one. We're doing a simple linear regression. Okay, so here, I'm literally just defining the variable x, which represents our input variables or the independent variables. And so in this case, we just have one, hours. Y is our dependent variable, which is the grade. So now I'm also going to add an intercept, remember, to the basic linear or the basic line that we learned up above. I'm adding an intercept to the equation, to our model as well, with this command right here, sm.add constant to x. So it's adding a constant to this, okay? So if we run this, there's a constant set to 1. Now that's been added into our data. So now we can finally estimate the linear regression using the sm.ols function, okay? We also need the dot fit in here to help find the beta hat and the alpha hats of our regression model. Okay, so let's run this. We can now obtain those model parameters using the params model method on model. Okay, so parameters equals model from up here dot params, and then we can print the parameters. So our constant starts at 68.79, and our hours is about 2.46. Okay, so meaning our coefficient from that regression, beta hat, is equal to 2.46. Okay. So let's look at this a little more clearly. Beta hat is equal to 2.46 and so on. And alpha hat is equal to 68.785. Okay, so this is our constant, and this is our slope of the relationship between the two variables. And so therefore, the slope of the line that best fits our data is equal to 2.46, and the intercept is equal to 68.79, right? So if we think back to those figures we just made up above, we're gonna have the intercept at 68.79, and then our x is 2.46, so a similar to slope to what we had before. Okay, so what do these numbers mean though? The alpha hat intercept suggests that if the number of hour studies is equal to 0, so we didn't study at all, your expected grade is going to be 68.79, okay? The beta coefficient now says for every additional hour of study per week, the expected grade increases by 2.46 points. So the predicted output value from regression can be computed as follows. Y hat equals alpha hat plus beta hat x, okay? In our example, using the alpha hat and beta hat computed above, we can compute the actual predicted GPA or y hat, okay, for each of our inputted values. So I'm just displaying the first 5 rows here. So here's the actual values, and here's the predicted grade that they would get from the regression model, okay? Now, we could alternatively use the predict method on the model to compute the predicted GPA. Okay, so let's do that. Model.predict x and get that added to our data frame. So here's an alternative hat, right? They produce the same numbers. This is just illustrating the point of 2 different ways to get our predicted value of what your expected grade would be based off of your study habits. Okay. Notice that these aren't always the same. Your grade isn't always equaling the actual predicted hat, okay? We're going to do some more with this. So let's plot these data points. The red line now, this is just the predicted grade at any given number of hours studied per week. And as you can see, our plotted data tends to follow this predicted grade pretty closely, right? The regression line appears to pass through the middle of all the data points. This is no coincidence. This is because the linear regression estimates the parameters alpha hat and beta hat such that the distance from these points is minimized, right? We called this distance error. So here to here, here to here, here to here. This line is going to plot the best line so that these distances are minimized, right? We want the error to be small as possible, okay? So below it, here is an example of the error for a single data point. Okay, I'm going to run this now, and we're going to look at what this figure looks like. Okay, so here's a single data point. The error for this is 85 minus its predicted value of 93.4, which is negative 8.4. So in a linear regression model, we actually represent this error using the delta symbol as follows. Okay. So now, after estimating the linear regression model, the error can be computed as the difference between the actual values of y and the predicted values of y. So error hat equals y minus the predicted value of y, which really just equals y minus alpha hat minus beta hat x. So now with this understanding in place, how exactly does a linear regression work? We're going to begin to understand the basic mechanics of this to estimate alpha hat and beta hat, okay? The linear regression model simply seeks to minimize the total error of the model, so the distance between those points. We represent this error as the sum of the squared error terms as follows, okay? So it's the sum of the error difference squared, okay? So of all of our values, this is the sum of the squared error terms, okay? Where SSE stands for sum of squared errors, the linear regression minimizes the sum of squared errors over a set of x and y of observations. Doing so provides the following useful formulas. We can now technically calculate beta hat and alpha hat. This is essentially what they're just equal to, okay? The bar over the variables represents the average value. Okay, so these bars are just the average values. Okay, so we can take the plotted values of x, or the given values of x, subtract off their mean, y subtracted its mean, and then take the sum of those values, multiply them, and take the sum of each of those values, and then do the same in the denominator where it's x minus x bar squared, sum of those values. That is what our beta hat is being calculated from. Okay. The stats model, so what we were doing up above, all this math that you're seeing here is being done for us. So this is nice. This is kind of like a black box behind statistical significance. Okay, we don't have to do this math. It's doing it for us, but it's helpful to understand the mechanics behind the model. Okay, so the next question now is, we've estimated a relationship, but does it even matter? Given the linear regression model we estimated, can we make any statistical statements about it, right? So we don't necessarily know if the hours worked translates to a better grade, right? We saw it, we've plotted the relationship, but we don't know if there's statistical significance. Okay, so this is going to depend on the error of the model. For example, what if the hours studied resulted in the following grades instead? Okay, so we're going to change our grades data frame slightly and re-estimate our relationship, get a grade hat. So this is going to be different than when we did up above, right? We have different values here. And we're also going to initiate a figure with two subplots. Okay, so let's run this line, these code, and see what happens with the new data. Okay, we still observe a positive association between hours studied and grade received, but there appears to be much more error than in the previous example, right? So the dots from the line versus where the dots are, the space between those, it appears to be farther apart, right? They're farther apart. So can we be equally certain that there's a relationship between hours studied and grades received from these two examples, right? So in this one, we're not quite sure, but this one, it looks pretty good. There's probably a confirmation of our hypothesis, right? Where hours studied is related to grade. Okay, so this is where statistical significance is going to come into play. Okay, so to help our learning of statistical significance, we can use the summary method on model to produce output that contains all the values we need to assess statistical significance. So here's how it would be done in our original data set, right? So the only difference that we have here is this dot summary function at the end. Okay, so let's run this, and voila. The summary, here's the summary. So I know this looks like a lot, but we really just need to understand a few key elements. I don't need you to know all of this, just a few of them, okay? And we'll be referencing back to this so that you can get a sense of what's going on. All right. So the coefficient estimates, we already discussed what 68.79 alpha hat represents, right? This is the constant term of the intercept, okay? So here it is. All that means is if I put in 0 studying, so if hours is 0, my expected grade is 68.75. And the 2.46 is now just a coefficient on hours. So for every hour I work, my grade should technically increase by 2.46 percentage points. Okay. The information to the right of these variables corresponds to the statistical significance of these coefficients. Okay, so let's talk about the first one, standard error. All right, the standard error value represents the standard error or variance surrounding the coefficient estimate, adjusted for the number of observations in our sample. So in our sample, we have 20 observations. Okay. The t-statistic, this is just equal to the coefficient estimate divided by the standard error. Okay, so for example, the t-statistic for the constant term is equal to 68.7855 divided by 2.677, which equals 25.69. That's our t-stat. Okay, the t-stat is what we use to determine the p-value in a t-table distribution. Okay, the p-value is derived using statistical methods that are beyond the scope of this class. However, we can understand its basic intuition. This is kind of what we fixate on as researchers, is the p-values, are the p-values. The p-values test the null hypothesis that a coefficient is equal to 0. In other words, it evaluates the assertion that there's no relationship between the independent variable and the dependent variable. A smaller p-value provides stronger evidence to reject the null, right? So if there is a relationship, we want to reject this null hypothesis that there's not. Okay, so the smaller the p-value, the greater evidence that you have that the null is not true, suggesting that a relationship likely exists. Statisticians often use thresholds or significant levels, such as 5% or 10%, to determine the strength of this evidence. All these thresholds mean that if the p-value is less than the chosen level, so 0.05 or 0.10, the null hypothesis is rejected, indicating that a statistically significant relationship is happening. Okay, so if the p-value exceeds these levels, then we fail to reject the null hypothesis, meaning that there is insufficient evidence to conclude that a relationship exists. Okay, so thankfully for the regression output printed above, the p-value for us, it's provided in that output. Okay, for example, the p greater than t, the p-value denoted by p is greater than or equal to the t statistic, absolute value of the t statistic for hours coefficient is equal to 0, which is less than 0.05. Okay, so that's a very, very low p-value. This suggests that this variable hours is significantly related to the number to improving your grade. Okay, so in other words, we find evidence suggesting that hours is statistically significantly related to grade. Okay, so other part of the model is the R squared. And what this tells us is how close the data are to the fitted regression line. So the definition of R squared is pretty straightforward. It's just the percentage of the dependent variable variation that is explained by the linear model. Okay, so an R squared equals explained variation divided by total variation. R squared is always going to be between 0 and 100%. 0% indicates that the model explains almost none of the variability in the dependent variable around its mean. And 100% indicates that the model explains all of the variability of the dependent variable around its mean. The R square of our model up above is about 63.9%. So in other words, we were able to explain roughly 64% of the variation in grade using only hours as the independent variable of interest in the model. Okay. All right. So, given this knowledge, can you perform and finish exercise 1? Okay, so pause this video, attempt this exercise, and see what you can come up with. So essentially, what I'm wanting you to do is this data frame 2 is related to the second set of grades that we did up above before. All right, so now, what is the coefficient on hours? That's what I'm wanting you to determine. And is hours significantly related to grade? So we just did this with the first data set. Now I want you to do it with the second data set. The other thing I want you to do is to look at the R squared of the model. How does the R squared of the model compare to the first R squared that we saw in the first model? And does this difference make sense to you? So again, pause this video and attempt this exercise. Okay. Hopefully I had a chance to do this. So I'm going to do the first little part with you and essentially just copy and paste code in that we did up above, right? Where data frame 2 is equal to the data frame we had previously. And I'm going to run this and estimate our ordinary least squares model, okay? And then print the summary. All right. So here, as we want to take a look at the coefficient on hours. So the coefficient of 1.3560 suggests that for every additional hour study per week, the grade increases by 1.356. Okay. However, the p-value on hours is much larger. So it's 0.257, which is higher than the conventional level of 5%, right? So given this, we have insufficient evidence to reject the null hypothesis that the coefficient is equal to 0, right? So that just basically means we don't know if there's any difference between 0 or not, if there's any sort of relationship between hours studied and your grade based off of this data, right? So in other words, we must conclude that there is no evidence of a statistical relationship between hours and grades, okay? Similarly, the R squared of the model is equal to 0.071. All right, this is much lower than the R squared of our original model. This makes sense because visually we saw much greater variation in the grade based on the hours, right? So if we scroll back up to this, we can see that the error terms or the distance between the actual values and the predicted value is much larger, right? We also saw that hours is insignificantly related to grade. So again, we have an independent variable in our regression that's not significantly related to grades, and so therefore it's not gonna predict the variation of our dependent variable of grades very well. So again, not much of the so our hours studied in this model suggests that the variation in grade isn't being explained much, right? So again, these are two different samples, right? And we came up with two different conclusions. One, we found a relationship between the two, this one, and the other, we didn't find a relationship between the two. So depending on the sample size and perhaps there's other factors involved that could be leading to this relationship of hours and grade that we're not controlling for, right? So there could be other factors within here. Perhaps the professor, perhaps the size of the class, so the number of students in the class. These sort of things could be influencing the hours that you worked, which therefore makes it hard to tease out a relationship, right? So when we get into multiple variables, we're going to start thinking about additional parameters that could go into explaining the variation of grade when it's important for us to determine if one relationship exists already. We need to make sure we control for other factors. Okay. All right, this is it. This is the video for today, for this day. Hopefully this helps with your basis of understanding of linear regression. We're going to go through this more in class. Okay.